Here is an example of using the node voltage method to solve a more complicated circuit that involves a supernode. This is an example again from the node voltage method packet that you have been working from in class. The first step when performing the node voltage method is to identify the essential nodes of the circuit. So again, what I'm going to do is go through the circuit here, and I'm going to determine where the essential nodes are located. Remember that an essential node is a connection of 3 or more elements within the circuit. I'm going to circle them and label them so I will have them as reference. So right here we have the connection between the current supply, resistor 1 and resistor 2. All right. So that is going to be an essential node. I'm going to call that essential node A. Right here we have another one. I'm going to call that essential node B. Right here we have another essential node, which I'm going to call C. And of course this entire bottom row right here connects all 3 of the resistors, the current supply, and the 12-volt power supply. So that forms yet another node, essential node D. The next step in using the node voltage method is to designate one of the essential nodes as being the ground or 0 voltage reference point. The one that makes most sense here, because it has so many connections to it, is node D. So I'm going to call that our 0 volt reference and say that the voltage at node D is equal to 0 volts. Now, we have 4 essential nodes, so nominally using the node voltage method we would need 3 node voltage equations. However, let's look at the circuit a little more closely. Nodes B and C, we notice, are connected directly with a voltage supply. We also notice that neither B nor C is the same as what we have designated as the reference node. When that occurs, we have what's called a supernode. So when that happens, what happens is that we reduce the number of node voltage equations that we need by 1. But when we do that, we add a constraint equation that's required. And we'll talk about how to get that constraint equation. The other thing that we notice is that this is not just an ordinary voltage supply. This is a dependent voltage supply that provides a potential difference that depends upon the current through resistor R1, and it's directly proportional to that current. So when 1 amp of current flows through R1, there will be 1 volt of potential difference between C and B. Since this is a dependent supply, we also need to add a constraint equation to determine the voltage potential based upon the current that flows through resistor R1. So all told, to solve this problem, we're going to need 2 node voltage equations and 2 constraint equations. Okay, so let's figure out how we're going to go about doing that. The first thing that I'm going to do is I'm going to isolate node A. Let me bring the circuit back in here, and let's look at node A. Okay, so node A is connected to this 4.8 amp supply. It's connected to the 0 voltage reference point through resistor 1, which is 7.5 ohms. And it is connected to node B through R2, which is a 2.5 ohm resistor. All right. And we want to write equations. We want to write an equation that tells us the voltage, how we can model the voltage at node A. To do that, we're going to invoke Kirchhoff's current law and assume that currents are leaving the node and that they are positive. So I'm going to call this I1, I2, and I3 through this path. Using Kirchhoff's current law, we know that we cannot accumulate a charge at any node, so the sum of all the currents entering and exiting the node must sum to 0. Here, since they're all leaving the node, they must all sum to 0. To rewrite the current in terms of the node voltages, first of all, I'm going to look at I1, which is right here. This is a 4.8 amp current supply, and it is flowing in the opposite direction of the assumed direction leaving node A. So for this, we can write that the current through 1 is given to us as 4.8 amps, and the negative sign indicates that it's flowing into the node instead of leaving the node. For the current through path 2, right here, through resistor 1, we know that the bottom of this resistor is at a 0-volt potential. So I'm going to invoke Ohm's law and say that the voltage at node A minus the voltage at the other side of the resistor, which is 0 volts, is equal to the current is equal to the voltage at node A minus the voltage at the other side of the resistor, which is 0 volts, divided by the resistance of R1, which is 7.5 ohms. The current through path 3, or resistor 2 right here, depends on the potential at node B, sorry about that, and the potential at node A. Since we're assuming that the current is always leaving the node, that means that under that assumption, for that to be true, the voltage at node A must be higher than the voltage at node B. So I'm going to write my current equation based on Ohm's law using that assumption. So VA minus VB divided by the resistance of the path, 2.5 ohms. Now I'm going to take those three current equations and plug them back into my Kirchhoff's current law equation that I established earlier. That will give us negative 4.8 amps plus the voltage at node A divided by 7.5 ohms plus the voltage at node A minus the voltage at node B divided by 2.5 ohms must sum to 0. And again, I'm going to algebraically rearrange this equation to read the voltage at node A multiplied by 1 over 7.5 ohms plus 1 over 2.5 minus VB times 1 over 2.5 is going to be equal to 4.8 amps. So this becomes my node A equation and one of the node voltage equations that I'm going to need. Now we're going to move on to node B. So I'm going to redraw node B. We have the voltage at node A connected through R2, which is a 2.5 ohm resistor, to node B. Node B is also connected down to our 0 volt reference through a 10 ohm resistor, and it's connected directly to the low side of the dependent power supply. Again, I'm going to assume that all of my currents exit the node, and those are going to be positive values if they're exiting the node. I4, I5, and I6. I'll invoke Kirchhoff's current law again, which tells me that I cannot accumulate any current at any node. So all of the currents must sum to 0. Okay. And then I'm going to use Ohm's law to determine how much current based on the potential differences and the resistance values. So this path right here is going to depend upon the voltage difference between VB and VA divided by the resistance of this resistive element. So I4, I'm going to go directly there now, VB minus VA divided by 2.5 ohms. The current through path 5 is going to be the voltage at node B minus the voltage at node D, which we're calling 0, divided by the resistance of that path. So VB minus 0 volts divided by 10 ohms. Now here we have a dilemma because we don't have a resistance across this path, but we do know that some current is going to flow through this power supply. how we're going to handle this right now is we're going to call that an unknown current. And I'm going to assume right now that this current leaves node B, and I'm going to call this the current that goes through the voltage, the dependent voltage supply 1. All right. Since I don't know what its magnitude is, I'm just going to assume it leaves the node, and I'm going to call it IV1. And all of that needs to sum to 0. Eventually, we need to get rid of that variable because we have no way of knowing what that is yet. So to do that, I'm going to turn to node C. So again, let's bring the circuit back into the picture here and look at what happens at node C. At node C, it's connected to the high side of the voltage supply, V1. It's also connected to R4, which is a 2.5 ohm resistor down to our 0 volt reference, and through R5, which is a 1 ohm resistor, to a 12 volt potential with respect to our 0 volt reference. Again, I'm going to invoke Kirchhoff's current law and say that all of the currents are leaving the node, and I will call this I7, I8, and I9. So Kirchhoff's current law again tells us that the current through this path plus the current through this path and the current through this path must all sum to 0. Earlier, I assumed and I called the current through this voltage supply, this dependent voltage supply, as being IV1. And based on the assumption here, I assumed that the current was leaving node B and headed towards node C. So what I'm going to do is I'm going to maintain that convention when I write this equation right here. So if the current leaves node B and I'm assuming that the current flows towards node C, that means that I7 must be the same magnitude as what was leaving B, but it's going to be going in the opposite direction. So I7 must be equal to the same magnitude as V1, as the current through V1, except it's going in the opposite direction as it was going here. So it's flowing into the node, so that becomes a negative sign. All right? I'm going to include that in the equation, and then I'm going to invoke Ohm's law yet again to determine how much current flows through this path as well as this path. So through path 8, it's going to be the voltage at node C minus the reference voltage, which is 0 volts, divided by the resistance of the path, 2.5 ohms. Here, along path 9, it's going to be the potential difference between node C and this 12 volt this 12 volt potential that's developed with respect to the reference node. So here I write VC minus 12 volts divided by the resistance of the path, which is 1 ohm. All that must sum to 0. Okay, so now, as I said before, we still have no way of determining what the current is in either of these equations through this dependent voltage supply. But we can use these two equations that we developed and combine them together to form one equation. All right, so if I were to solve this for IV1 and plug it back into here, I would get a combined equation. I'm going to take these two and put them together. I would get a combined equation that looks like this. VB minus VA over 2.5 plus VB minus 0 volts over 10 plus VC minus 0 volts over 2.5 plus VC minus 12 volts over 1 ohm must all sum to 0. This is our supernode equation. So this is the second equation, or second node equation, that we're going to need to solve the system. Okay? You see that we took two nodes and we combined them into one. So we lost some information about what happens between node B and node C. And we'll have to write a constraint equation to compensate for that, and we'll get to that in just a second. Knowing that I'm going to wind up with a system of equations, what I'm going to do is I'm going to rewrite this equation, the supernode equation, to accommodate a matrix solution. So when I rearrange it algebraically, I wind up with something that looks like this. Volts over 1 ohm. Okay, as I said before, by combining these equations, we have lost some information about the relationship between the voltage at node B and node C. So to make up for this, we have to come up with a constraint equation. All right. The relationship between node B and node C is actually given by the dependent voltage supply itself. So I'm going to work on the constraint equation. All right. We know that since there is a voltage supply between nodes B and C, that the potential difference between node B and C must always be related by the amount of potential that is developed with this voltage supply. Okay. To note that the voltage at node C is always going to be higher than the voltage at node B by the amount that this voltage supply provides, we can write a constraint equation that tells us that. Since this is the positive side of the voltage supply, we know that the voltage at node C is going to be higher. So the potential difference between node C and node B is going to be that of the power supply. So VC minus the potential at node B is going to be equal to 1 volt per 1 amp, that's the gain factor of the power supply, multiplied by the current through R1. Or alternately, we can rearrange this and say that the voltage at node C minus the voltage at node B must be equal to a gain factor of 1 multiplied by the current through resistor 1. And again, since I'm going to be using some type of matrix solution here, I'm going to rewrite the equation, say, to be of this form. Minus VB plus VC minus IR1 needs to be equal to 0. Okay, so we have two node voltage equations, one from node A, one from the combination of nodes B and C. We have one constraint equation. We need yet one more constraint equation as we determined in the beginning. All right. This final constraint equation needs to relate the current through resistor 1 to the unknown node voltage. This is a pretty simple task. We know that the voltage at node A is VA, all right, and we know that if we know that voltage, we can also calculate the current through resistor 1 using Ohm's law. The relationship there is that the current through resistor 1 is equal to the voltage at node A minus the potential on the other side, which we've called 0, divided by the resistance of the path. And again, I'm going to rearrange this equation so that we can put it into our matrix solution form. That results in VA minus 7.5 ohms times the current through R1 equals 0. We have two constraints and we have two node equations. So now we have everything that we need to solve the system. So let's review that. We have from node A, we have this equation. From the combination of nodes B and C, we have the supernode equation. And we have the two constraints that we just developed. All right. What I'm going to do now is I'm going to rewrite all of those equations in a matrix form. So you can see the final solution process. R1. This equals 4.8. This is equal to 12 amps. And both of these are equal to 0. Okay. So writing it out in this form, all of the equations that we developed, the node equation, the supernode equation, and the two constraint equations, we clearly see that this is a system of equations in 4 unknowns: VA, VB, VC, and the current through resistor 1. We can solve this system simultaneously by whatever method you prefer, and when we do that, we get the solution that the voltage at node A is equal to 15 volts, the voltage at node B is equal to 8 volts, the unknown node voltage at C is equal to 10 volts, and the current through resistor 1, although we don't necessarily need to know that, since it was in the equations, we get that value to be 2 amps. So again, by developing those 4 equations, those 4 simultaneous equations, now we have completely solved the circuit because we know the voltages at the primary or the essential nodes. From those essential nodes voltages, we can calculate the current through any of the branches in the circuit.